Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be exploring the topic of factoring by grouping. Again, we're going to try to answer the question, how can we determine the factors of a particular polynomial without knowing either of them? And we're going to try to answer this by using this idea of grouping. Now first, let's demonstrate an example of when to group with polynomials. Notice that in this example, we have a four-term polynomial. The terms are x cubed, a negative 3x squared, a 2x, and a negative 6. And we want to find what two polynomials multiplied together to get us this. In the previous video, we discussed the topic of the GCF. And we said hopefully there would be a GCF in your polynomial that you could factor out and see what would be remaining. However, in this case, there really isn't a GCF. Look at the numbers, or the coefficients, I should say. 1, negative 3, 2, and negative 6. Really, the only number in common with them is a 1, and that really doesn't do anything when we factor that out. And then let's look at the variables. Well, there's 3x's here, there's 2x's here, there's 1x here, but there are no x's here. There are none. So therefore, there isn't a common variable that we can work with. So it would be helpful to point out here that the GCF doesn't exist. Instead, we're going to need to come up with an alternative method for breaking this down to find what the two factors can be. This technique is the technique called grouping. While there does not exist a particular GCF for the entire polynomial, what we can say is, let's try to form two separate groups of this polynomial. Let's split it up. So I've paired together the x cubed and the negative 3x squared, and I've paired up the 2x and the negative 6. Our hope is, while there's not a GCF for the entire polynomial, maybe there's going to be a GCF for parts of the polynomial. In the first section, let's take a look at x cubed minus 3x squared. What is the GCF here? Well, hopefully you're noticing that the GCF is x squared. The numbers don't have anything in common, but there's at least two x's in both expressions. And then let's take a look at the second pair. What is the GCF here? Again, hopefully you're noticing that the GCF between 2 and 6 is 2. And there's not a common variable, so we don't need to worry about that. So the GCF of the first part is x squared, and the GCF of the second part of the second group is 2. What we're going to do with this is, I'm going to factor out the x squared from the first group. So when we divide out an x squared from everything, we're left with an x minus 3. And I'm going to divide out or factor out the 2 from the second group. So when I factor out a 2, we're left with an x minus 3. You can go ahead and check your work. If we went and redistributed each thing through, we get an x cubed minus 3x squared, and we get a positive 2x and a negative 6. So it works out. This type of factoring, where we don't pull out a GCF from the entire thing, but where we pull out GCF from groups of the entire thing, allow us to rewrite the polynomial. So here's where we ended up. We said that we could rewrite the polynomial as x squared times x minus 3 and 2 times x minus 3. The GCFs have been factored out. What do you notice now about the polynomial? Make sure you realize that this is one expression and here is another. We have two components here. What do both of these components have in common? Pause the video, try to work out your idea about what these both have in common, and see if you can write the final answer. Well, hopefully you notice that both of these expressions have an x minus 3 in common. That's in both of them. And x minus 3, remember, that's one thing. That's part of this larger expression, okay? So let's go ahead and let's try to factor out the x minus 3. Let's divide x minus 3 out from each of these expressions. So when I pull out an x minus 3 from the first expression, what are we left with? An x squared. And when I divide out an x minus 3 from the second expression, we're left with a 2. Here is our final answer. X minus 3 times x squared plus 2. What we've done is we've gone through and divided out each of these x minus 3's. We kind of, I'm going to use a made-up word here. It's like we're undistributing, right? I know that's made up, but we're kind of doing distribution in reverse. We're pulling the x minus 3 out, okay? Hopefully you can see that, because let's go ahead and let's try to simplify this answer that we got. Let's check to make sure that it actually works, okay? If I have x minus 3 times x squared plus 2, I can take this entire expression and distribute it through. This is what we learned when we went over multiplying polynomials. So we have x squared times x minus 3 plus 2 times x minus 3. What do you know? That's exactly what we had before. And then, as we keep going, we get an x cubed minus 3x squared and a 2x minus 6. We get back to our original polynomial. Hopefully you're seeing that this process, this idea here of grouping, where we don't have a GCF for the entire polynomial, but we have GCFs for components of the polynomial, is basically allowing us to show that there is a common factor still embedded within, okay? If you've got a 4-term polynomial that you need to factor down, 4 terms, if that's what you need to factor down, you must have multiplied 2 binomials to get that. So to find those two binomials, factoring by grouping is really going to work for us, okay? Now, will factoring by grouping always work? Is that always possible? Not necessarily in the real number system, okay? This is just an extra technique that we can have. We said before, the GCF method might work and it might not work. It won't always. Same thing with grouping. Grouping might not always work. Okay, you might be factoring things out, and these might not be the same values. You might not have the same polynomials in both of them, right? You might have had an x minus 3 and an x minus 5, whatever. The idea here is that when it works, this is what we want to see, okay? Will it always? No, but if it does, this is what we want to see. Let's get a procedure written down for this. Step 1. Group together the first pairs and the last pairs. Okay, we grouped together the first pair of values and the second pair of values. After those have been grouped together, we need to find the GCF of each group. When we do that, we factor it out. So find the GCF of each group and factor it out. And that's what we did at this step right here. We found the GCF for each pair, factored it out. Okay, remember, factoring out is same terminology as dividing it out. Once that has been factored out, we should, I'm going to underline should, see a common binomial. Factor it out. Okay? In this case, the x minus 3 and the x minus 3, those were the common binomials. So we need to factor those out, okay? And once we factored it out, we would see what we were left with, the x squared and the 2. So once you have factored out the common binomial, write the product of that binomial, I'm going to abbreviate that BI. So write the product of that binomial and what's left. So the quantities that are left over. So here was the binomial, and here what was left. So that's the idea of factoring by grouping. Let's keep practicing this technique in a couple other problems, and then let's try to identify when we want to go about using this. So first up, let's take a look at this problem right here. We have a 6ab minus 21a plus a 4b and a minus 14. First off, we should probably ask ourselves, is there a GCF in here? That old method that we had before, let's see if it could work. Is there a GCF? Well, we have a 6 and a negative 21. The only thing in common with that is the number 3. But then we have a 4, and 21 and 4 don't have anything in common. Neither do, well, 21 and 14 have 7 in common. But yeah, there's no GCF in common with all of the numbers. What about the variables? Well, there's no A in these problems, so they're missing an A. This one's missing the B, and so is that one. So really, no, there's nothing in common here. There's no GCF. The variables aren't all common, and the numbers don't have anything in common. So instead, we're going to have to use our method of grouping. So let's go ahead and try to group this. I'm going to put parentheses around the first two values, and I'm putting parentheses around the second two values. Please note here that I have not included the plus sign, okay? That's in between the parentheses. I want to make a quick side note to us here that 6ab minus 21a plus 4b minus 14 is the exact same thing as 6ab minus 21a plus 4b minus 14. That should be pretty obvious. It's all really just addition and subtraction, so by me throwing in the parentheses, that really doesn't change anything up between these, okay? What I am not saying is that these are equal to 6ab minus 21a and then the 4b minus 14. These are not equal to each other, okay? Because this implies multiplication. If you didn't put that plus sign there, you would be saying, let's multiply these together. That is not what we have here, so do not go about doing that. Always make sure you include that plus sign in between, okay? Let's clear some space now and actually go through that grouping process. So first up, we go ahead and we have separated the values into the two groups. Now what we have to do is identify what's the GCF from each group. So here we have 6 and 21. Well, a minute ago I said the only factors that those numbers have in common is the 3. And then let's take a look at their variables. Well, B's not in common between the two, so the GCF won't include B, but they do both have an A in them. So we can go ahead and say that the GCF is 3A. For the second group, we have 14 and 4. Well, both of them have 2 in common as a factor, and there's no variables in common, so the GCF is just going to be 2 here. So what we're going to do is we're going to rewrite this polynomial by first factoring out the GCF of 3a from the first group. So when I divide 3a out from everything, I should end up with a 2b minus 7. I'm asking myself, what times 3a got me to 6ab? Well, that was 2b. And what times 3a got me to negative 21a? That was a negative 7. Or you could just go ahead and just divide each thing. Hopefully you're getting this idea of how we're dividing out the GCFs. And then, same thing as before, when I factor out a 2 from each of these, well, I had 4b, and when I factor out a 2, I end up with 2b. And then I have a negative 14 with a 2 factor out is negative 7. Again, check your work. Make sure you're doing this correct. Just redistribute everything and see what you get. You should get the exact same answer back where you started. Now, Let's go ahead and see what we notice here. Both of these expressions have 2b minus 7 and 2b minus 7. So we can factor out the 2b minus 7. Let's divide that from everything. So we'll end up with, well, we factored out the 2b minus 7, so what were we left with? A 3a. And we factored out the 2b minus 7 here, and what were we left with? A 2. It's almost as if we can note to ourselves here that there was a GCF in this original polynomial. It was 2b minus 7. We just couldn't see it before. So what grouping does is it forces us to see what was distributed through. I guess what would that GCF be? So here is our final answer. You can use box method to check your work, but you would be able to see that this is what we're going to get. Now, when do we use this technique of grouping? Well, we are going to say that grouping is going to work, and we're going to use a lighter definition to this, but we're going to say grouping will work when you are factoring 4-term polynomials. If you're going to factor a 4-term polynomial, try grouping, okay? Will it always work? No, it won't, okay? In some cases, especially in the real number system, when you try to use grouping, it's actually not going to work out, okay? And could we use grouping for other types, other sized polynomials? Yes, there's ways of doing that, but really in this class, and in most future algebra courses that you're going to be working in, we really only use it for 4-term polynomials. So if you see a 4-term polynomial, I want in your head the light bulb to be clicking that, oh, we should be using grouping for this, or at least trying it to see if it works. Let's go ahead and let's try another practice problem. In here we see, what type of polynomial is this? It's a 4-term polynomial. So the light bulb in our head should be clicking, wait a minute, 4-term polynomial, I should be thinking about maybe grouping this. Obviously we can see there's no GCF in here. There's nothing in common between the x squared, the 5x, the 2x, or the 10. So really, we can't factor out a GCF, so our only hope right now is to maybe try to group this, okay? Now, let's go ahead and put our parentheses in. Notice that I'm still trying to leave that plus sign in between the parentheses. And let's try to identify the GCF of each group individually. So we have an x squared minus 5x. Well, there's nothing in common with the numbers, but we can say each term has at least one x in it. And then for the 2x minus 10, we can say that, well, at least each term has a 2 in it. So let's factor out these GCFs. When we pull the x out, or we divide the x out from the first group, we're left with an x minus 5. And then when we factor the 2 out from the first group, we're left with an x minus 5. Again, they have the same binomials, x minus 5 and x minus 5. That means x minus 5 must have been distributed through x plus 2. What was left over? Hopefully you're starting to get this process down, and really hopefully you can see how we took this binomial and distributed it through to the other one, okay? That was a technique that we had back from the algebra of polynomials. And this right here is going to be our final solution for this problem. Now I wanted to point out, because the students have asked me in the past, you set this problem up as x squared minus 5x plus 2x minus 10. And then they would say, you've also told us that addition is associative, meaning you can add in whatever order you want. And you can add negatives in whatever order as well. So what if we rearrange it to have the positive 2x here and the negative 5x here? Could we still factor this down and get the same answer? Or did it have to be in this form that you gave us? Let's take a look and let's see if that affects it at all. Now, when we go about factoring this, notice that I am going to be grouping this just like before, and instead this time I'm going to include the negative sign inside of the parentheses, and I'm still going to put a plus there, okay? Notice that these are the exact same thing. I could write plus a negative and still be the same thing as minus 5x. You have to include the negative inside of the parentheses. Again, let me take a minute to explain why. If I wrote this, where I had the negative on the outside, suddenly these are not the same thing. Because this would imply I'm going to have to distribute a negative through to get x squared plus 2x minus 5x plus 10. That is not what I had at the beginning, okay? So make sure you still have a plus sign in between the two and you're including that negative in the parentheses, okay? So let me clear some space here and let me get back to this grouping. And I'll reset it up where I have the negative on the inside. Always make sure every step that you take here, you should be able to get right back to where you started. Now, I've got my group set up. The first one only has a GCF of x. This one, let's see, what's the GCF here? Well, between 5 and 10, I could say it's positive 5, okay? But think back. Remember when we talked about GCFs? If that initial term is a negative, we might want to make the GCF also negative. So let's see what would happen if I said, okay, GCF between 5 and 10 is 5, but since it's negative 5, I'm going to make the GCF also a negative. Let's see what happens when we do that. When I factor out the x, in the first group I'm left with an x plus 2. In the second group, when I factor out a negative 5, I divide negative 5 by everything. I'm left with an x and a positive 2 again. Remember, negative 10 divided by negative 5 is positive 2. So this is what happens when I factor out a negative GCF. If I didn't do that, right? If I factored out a positive 5, let's see what we would have there. If I factored out a positive 5, I would have been left with a negative x and a negative 2. And I would have been stuck because these are not the same thing. Okay? What we really need to do here is be comfortable with this idea of factoring out negatives. Okay? Our trick is do that anytime the leading term is a negative. Then you can make your GCF negative, okay? So we'll see here that we have a common binomial. We can factor that out. And what's left is an x minus 5. Again, we get the same answer as before. You'll notice in the previous problem, the common binomial was x minus 5. Here, it was x plus 2. And that's okay. All we did when we swapped around those terms here was we were showing that essentially we're changing the order of the multiplication. Instead of x minus 5 times x plus 2, we did x plus 2 times x minus 5. Does that matter? Does order and multiplication matter for polynomials? No, it doesn't, because polynomial multiplication is commutative and associative, so you can multiply in whatever order you want and it'll still work out, okay? Hopefully this technique of grouping is making sense to you. We're starting to get a little more abstract in our techniques, but that's okay. If you have any questions or comments about the video, please let me know. My email is klinford, that's KLINFORD, @wccnet.edu. Let me know you thought of the video or any questions that you have, and until next time, take care.